This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. Developers, are you ready? It's time to upgrade your data platform to InterSystems Iris. Choose your language. Choose your tools. Choose your environment. Collaborate, build faster, and deploy more efficiently. When you can make faster decisions, there's no telling what you'll create. Ready, set, code. Start coding for free. Visit intersystems.com/try to try Iris.
For Software Engineering Radio, this is Robert Blumen. I'm joined today by Rob Skillington. Rob is the CTO and co-founder at Chronosphere. Previously, he was a technical lead on the observability team at Uber for M3. And Rob is the creator of the open source M3 platform. Rob, welcome to Software Engineering Radio.
Thank you for having me, Robert. It's great to be here and great to get a chance to talk.
Rob, today we're going to be talking about monitoring and alerting at scale. Before we get into the at scale part, I'd like to do a brief overview of monitoring and alerting, starting with monitoring. What is monitoring anyway?
Yeah, great question. You know, at one point, I referred to it as keeping computers running in a very generic term, but the the more technical, kind of term is really how just thinking about how software runs, making sure that it's up, that it's healthy when you're talking about a service, and it kind of all the parts of really measuring the health and performance of a system, whether that's a box product piece of software or an online service or an embedded piece of hardware. Monitoring really means the same thing everywhere. It's about being able to observe that and measure the health and performance of a system in question.
How does alerting fit into that?
Yeah, so alerting is definitely been around for quite some time. Nagios is an open source system that harks back to definitely more than a decade old, probably multiple decades old at this point. And that really is a great piece of software for monitoring online services and has been for quite some time. But that's kind of really where we came from. And while it's obviously super still used and relevant, it's still, I guess, like the way that most things were done before in an online sense, which is like you run a bit of code that probes a system, and that probe returns a result. And then you kind of have this like check or fail view of the world, pass or fail rather, in terms of whether a system is up or down. And then, you kind of add more and more probes, so you can kind of probe more things. And then you have this kind of pass or fail view of a lot of independent parts of a bigger system that helps, you kind of make a decision on whether you think something is healthy or not. And that's has been very popular for a very long time. And then today, we're seeing a lot of time series based monitoring going on, as well as looking at, like what's happening with the log output of your systems and kind of analyzing that data. But, fundamentally it's moving, I guess, away from probe based to really contain many other more complicated kind of signals coming out of these systems as well, such as time series based data and log analytics.
If I understood that, then a probe would be we're going to check something and either maybe it doesn't come back at all or comes back with a bad result. That's a fail. Whereas time series, you could have a more sophisticated condition that looked at a series of points over a 5-minute window. And you might have a single bad data point in there, but that wouldn't necessarily be a fail.
Right, exactly. It lets you look at things more volumetrically. So, if you were measuring the electricity output of, an electrical component that was speaking binary maybe between 0 and 5 volts, it's a lot more granular you don't just see 0 or 1. You see exactly how many volts are coming out of that component. And the time series is, kind of like a graph of that signal.
What happens when there's a fail?
So, when you're talking about time series analysis, there's usually a lot of thresholds that are put in place. So it's either you have some time series that you're analyzing, perhaps there's some summing across different, actually multiple compound time series to, present a final time series that you would put a threshold on. But usually it's about declaring that the fact that you want to make sure a certain time series either doesn't go below a certain value or doesn't go above another value. And then, when it fails or fails that precondition that you're trying to hold the time series to, then typically on call engineers who would be on call for a system would get paged. So that's either, using something like some kind of service like PagerDuty, which allows you to set up a roster, and then when an actual event happens that it requires investigation, you would kind of have your system tell PagerDuty about it. PagerDuty would find the person on call for that roster and then kind of page their phone by giving them a call, or ping their app or send them some kind of message to let them know that they need to acknowledge an incident needs to be looked at and resolved. But of course, you can do that with Nagios probe-based checks as well. Probe fails, send a message to some system and have that system notify a human to go look at something.
The purpose of that then is to involve a human in the operations of the system to possibly fix something that won't fix itself.
Right. Yeah. A lot of the time it's, and this is actually a super interesting topic we could talk at length of, but it's really, this is where the human element part of this is fascinating, because you really want to alert on things that actually matter. You could probably set up 1 million alerts if you were wanted your system to exactly react and perform in some way. But really, it comes down to how's your actual system behavior performing, because that's what you really care about. You don't really care that it took an extra half a second sometimes to do something else if that doesn't really matter to what your end system is actually doing as a unit of work. So it's a lot about kind of setting parameters on things you care about, and then involving a human when that's necessary. You can use alerts as well, though, for also auto remediation or automation. For instance, like you could set up in fact, I know a lot of auto scaling is done this way, right? Like you set up an alert that when either CPU or some other threshold is exceeded, you fire a webhook, and then some system that receives that webhook will go and perhaps scale up your cluster if it's kind of within a certain, you obviously need to put in some protection mechanisms there. You wouldn't want to infinitely scale it up, but then, it allows for automation to actually react to, so systems to react to change that's going on in the underlying system based on signals that your monitoring picks up on. So most of the time it's involving a human. Sometimes, though, it's also automation kind of dealing with the output of one of those alerts or alarms.
Monitoring, we're going to be talking more about concept of a metric. Tell us what that is.
Yeah, so great. That's a really fascinating question. I mean, in terms of what day to day we work with in the monitoring world, a metric is really a type of event that you are tracking. I guess that's pretty applicable to most other subcategories of computing as well. It's really, when I think about what makes up a metric in the monitoring world, it is a schema. It's a type of event that happens, and it's the different dimensions that separate the types of events. So to give a concrete kind of example here, if we think about HTTP requests, to me, the HTTP request returning a response, that's a metric, because that's the event that's happening. You're returning an HTTP request to an end user. And then, so that's the event. And then on that metric, you have dimensions such as what is the endpoint that was served. So what was the URL pattern that your handler got called on? What was the status code? So was that, in the 200 range, the 500 range, or the 400 range, and then things like what is the server software that served that request. So all those are dimensions on an underlying metric, which is describing an event. But, I will say that it's not always events. A lot of the time as well, it can be volumetric signals. So CPU usage, network throughput, how many megabytes or megabits per second you're sending over a network, and memory usage. All of those are very volumetric. They're not really events per se. They're kind of like a point in time data point that you measure.
Is the metric this collection of dimensions and values, or is there a single value that's the metric and then all these other dimensions are, let's call it metadata or labels?
Yeah, so the way that we really like to kind of structure it in terminology is thinking about, the metric being kind of the type of thing you're measuring, so event or some sampling, and then the combination of dimensions makes up a time series. So, for instance, like going back to that HTTP request example, we have, for instance, a single time series that is part of an HTTP request response is an HTTP request response that was served a 200 status code on the /health URL. So that's one time series. Another time series would be the same metric name, and then the dimensions would be 500. So internal server error being returned from the path /health. So time series are the underlying different event streams that are identified by their unique dimension values. And then event is really the category, all of those time series being classified as meaning one thing that you're measuring, or one class of events or component that you're measuring, if that makes sense.
So we apologize to the listeners. Rob has just told me it started hailing where he is, and he's moved into another location further away from the window. So should be better for the rest of the podcast. Back to where we were. You have these metrics and they have dimensions which have names. How do you define in a computer system the alert on top of these metric values?
Yeah, so that's a great question. Basically, you can think of when you're kind of building an alert, a lot of the time you want to see what the historical failure or pass and fail rate is going to look like. So, and you can actually imagine with, when we're talking about those probe-based events, that's a bit harder to do this because you don't have any signals coming out of the system. You're literally writing code that may pass or fail based on what happens with the probe. Whereas with time series data, and looking at metrics, when you create an alert, you're fundamentally adding a threshold to basically capture whether an alert would go off or not based on signals you already have that you can see in a graph. So typically what you do in, you author an alert is you go and look at all the different signals that are coming out of your system in a graph. Maybe you apply some functions to it. So, maybe there's some spikes that you want to kind of smooth out because you don't mind if, CPU jumps to 90% just for a short burst. So you might want to do something like average over time or like a moving average. And then, so you can actually apply transforms on top of these time series as well. And then finally, you kind of put in your thresholds for where you may want to actually alert on that transformed signal that's coming from your system. So typically what you do, when you're writing these alerts is you start by graphing and visualizing the different metrics and underlying time series that you're kind of want to alert off of. And then you come up with a graph that makes sense to you logically on the type of thing you're trying to do. So you may, for instance, it's very easy to say, I don't want any internal server errors to be returned to my users. Otherwise, tell me about it. And so, a very simple alert would just be take the number of times you return an internal server error for a given set of HTTP endpoints, and whenever that exceeds, 0 or some reasonable threshold, if that's something that you need to do given the behavior of your system, and then set that threshold, and then finally, depending on the monitoring system you're using, you may go to a config file if you're using Prometheus, which is a popular open source monitoring tool, and save that rule to the config file, and then either redeploy your system or cause a reload to occur by calling an endpoint. Or if you're using a vendor, you'll probably go to a UI or use some command line utility to kind of update an alert definition. So that's typically the life cycle we see when you kind of author these alerts.
I want to wrap up our general discussion about monitoring and alerting and talk more about our main point, which is at scale. So what does it mean to have monitoring and alerting at scale? What are the challenges that start to emerge? I could see if you had a small number of alerts, it'd be possible for one person to know everything about it. But what starts to break when you get into larger systems?
Yeah, good question. So the main thing, at scale that tends to happen is your system gets more complex. Whether that's your product getting more complex, or fundamentally you're scaling out the team, and the team to support some product line needs to refactor the code in such a way that is more complex. But typically, one of the two are happening, and you have just a lot more code paths now to track. So in regards to kind of monitoring that, you need to think about all the different things that can go wrong. I would start with really, though, just defining what your SLAs are. What are your service level agreements? What is the things that when you break a contract, you will get a customer or user or your manager upset. What will upset them essentially? What do those contracts look like? And then essentially putting alerts on those. And then in a more complex system, what tends to happen is that you have the layer that interacts with the end user, but then you have layers below as well. So you'll have like a data layer, and that data layer may have a contract with other developers inside the company that it should return reasonably within 50 milliseconds or something like that, a record about a user or a record about some object. And so you really think of it like laying down your monitoring in terms of layering on the layers of an onion. And so at the most core layer, you do want some alerts as well, and at the medium, and then at the most important are the SLAs and the contracts that you actually have at the very edge of your system. But you want to know ahead of time when things closer to the lower level start to misbehave, because that can cause a cascading failure and kind of impact all of your product or system at the higher layers. So typically what tends to happen when you scale out is you need to cover more HTTP endpoints. You need to cover more server versions that you're tracking are in production. You probably have more either VM instances or machines or containers running your software. So you have many more points of failure. And you want to basically make sure that when you do get an alert that goes off, you can drill down exactly to which one of those points was a failure. And so fundamentally, you're just adding dimensions to a lot of these metrics, whether it's because you have a more complex product or because your infrastructure is more complex. And then it really comes down to how do you deal with that level of complexity and scale of the monitoring data, and do you do that in a way that's sane, or does it become unmanageable and it's just a mess of alerts and no one really can understand what's going on because you're not doing it in a clean, consistent manner across your system. So that's some of the things to really think about, and some of the common things that become problems very quickly. And if your tools are working against you and you can't just kind of collect more monitoring data, and you can't if that's problematic or cost ineffective because it's too expensive, or perhaps there's just frictions there that is hard to use. Maybe your query language for querying these time series is super obtuse and not well documented, which is why we love open source software in this space. I'm an open metrics contributor, which is a standard here in this space, and I think that you really want your tools to work with you, and you want there to be some knowledge and nomenclature that's common to what you're doing amongst the team. And that depending on the tool you're using, whether that's some very niche specific vendor tool or some very common popular open source tool, or a mix of the two, you really want to think about that as well as you start to scale up your monitoring needs.
On a number of points there, some of the main takeaways for me is as the system scales up, you simply have more metrics because there are more things to monitor on and more things to alert on. And then you have a lot more data, which is going to create load on the monitoring tools. And if you have a database in your monitoring system, you mentioned that this manifests as more dimensions. And what I think you're talking about is, let's say that all your services are HTTP. And if the service which originated the metric, if that is a dimension, then that manifests as more values in the given dimension. Did I get that right?
Right, yeah, and especially if you're playing in a Kubernetes world or some kind of container system, it's not even just a service; it's a service and then the underlying process ID. Because of course, if you run 200 instances of a single service on really small containers, when something goes wrong, if it's hyper localized to just one of them, you kind of need that dimension of which container was running it to be able to localize the problem and kind of quickly go from an alert to debugging your application.
We're veering into this topic, which I wanted to cover, the idea in monitoring of high cardinality and high dimension monitoring, which is something you told me that you wanted to talk about. I'll let you talk about that now. What do you mean by that, and how does that relate to scale?
Yeah, great question. And thank you for let me kind of bring it up. I mean, a little bit to what I was kind of talking about previously with what happens, as you start to scale up a complex system or an engineering team that's working on a system that starts to accrue a lot of complexity in it. What typically tends to happen is it starts to look like a bowl of spaghetti from the outside if you can't really see what's going on. And a lot of people start with like reading the code, right? But at a certain level, and even with 3 or 4 engineers or developers, you can reach a point where that's just inefficient, essentially. And honestly, when you're encountering a failure in a system, the last thing you want to do is go read the code. You want to mitigate the problem first, right? And logs is typically, being very useful here. But with the, kind of change which is happening out there, that's seeing a lot more things run on ephemeral environments in the cloud. And, more people are using lots and lots of containers instead of a few VMs. And people are also using distributed systems more frequently, where they would have had just one monolithic system. Microservices are becoming more popular. I think you have to be really careful with how far you go in that direction, and I have stories on that. But it technically, really what the kind of trend that I'm talking about here, though, is that essentially you really need some direction at a higher level than just thinking like, I have a problem, I need to go look at the logs or read the code. Like it's kind of already, it just takes so long to perform that analysis that, when you're trying to mitigate a problem or understand even just how a larger system is working at a higher level, you really need a lot of signals coming out of that system that makes sense to you and makes sense to others without having to go and deep dive on a specific set of logs or try to understand how a flow, a code path is working based on the code. So high dimensionality metrics is really about giving you those signals at higher and higher levels of granularity, so that when you do trigger an alert, it's not just telling you that you've got a spike in error rate. It's telling you you've got a spike in error rate. There's a specific HTTP endpoint that's exhibiting the problem, and it only happens with the new version of the code you rolled out, and only with clients that is, if we talk about an example where you're using a mobile application and serving traffic to a mobile application, it's only, you're only seeing an error rate with the new code with a mobile client of a specific version or operating system. So all those extra caveats there helps you get to your root cause much faster. Having those extra dimensions and those extra signals that gives you depth into the problem or how the system is just behaving in general is super helpful, and that's really what when you keep adding those dimensions, that's what causes high cardinality, because high cardinality is really talking about the number of unique time series. It's not talking about the metrics. You might still be tracking the same type of things, but the number of underlying time series explodes because you want to slice and dice on a high number of dimensions.
Hiring a software engineer? Then we recommend working with G2I. G2I is the most effective way to discover talented and pre-vetted engineers for every project. G2I vets their talent pool through technical interviews and various code challenges which are graded by actual engineers, saving you time and guaranteeing you top quality through their transparent grading. They specialize in React, React Native, and Node.js. Interested in learning more? Then go to g2i.co.
If I averaged everything together, it might look fine. But what you're saying is if I was able to see this given metric of a latency and to group it based on user agent, the endpoint it's hitting, whether it's a mobile or fixed code version, and let's add 3 more things. And you might see that out of that big high dimension space that one of them is behaving very badly, and that set of users is having a terrible experience, which I would not see if I averaged it all together.
Right, exactly. And a concrete example here is, at Uber, we would have these type of things where certain telecom providers would go dark with the routing to our backend, and sometimes it was the routing to our backend and not all internet websites. So it's like, if you're on AT&T and you're in some part of the US that's experiencing a routing issue to a network server that was hosting Uber, you may be impacted, and that's a terrible user experience. Like, if we don't want, especially at the company, we wouldn't want specific both users of the system to experience a hyper outage like that for potentially days at a time. We need to know about that, and when you just have user reports from the wild, it's really hard to correlate that. So even just by adding a dimension of what telecom provider it looked like an IP address was coming from, as well as certain things around where the mobile client was pinging in from, that helped a lot to try and get to a root cause much quicker and understand a root cause. And then when you think about like Netflix, they talk about this problem as well, where they can tell that a specific iOS version in Brazil watching a certain title is not able to play back a MP4 file that they've encoded slightly differently to all the rest. So that level of diagnostics is kind of required in this world that's growing like more complex, and also just honestly makes for it a lot easier to actually see what's happening. Yeah, in that, when you were talking about averaging everything out, like if you just looked at how many playback failures happened for that one TV show on Netflix, you might not see the fact that this one specific iOS version in Brazil is experiencing a hyperlocal problem. It might just look like less than 1 or 2%, who cares? But that's really actually an underlying problem that can be fixed if you know what the root cause is and you can kind of drill down quickly.
I think now you haven't said this, but I am inferring this from what you said. So the cardinality is the number of different values you can have on a metric, and then the dimension is the size of the overall space when you multiply all these cardinalities together. Did I extract that correctly from what you said?
Yeah, I would really probably think about it just as metric made up of many time series influenced by the dimensions. So like multiplying the unique dimension values together gives you number of time series for a metric. And then the cardinality is really just the number of unique time series. That's really the same thing. So that's how I like to think about it.
Okay. And if we're going to be talking about high cardinality, could you give us some numbers or orders of magnitude in a organization like an Uber or a Netflix? What are we looking at here for how many unique time series, how many distinct values are there? I could guess for countries you could have dozens or 100. Give us some concrete numbers.
Yeah, definitely. Yeah, I'd love to do that. Yeah, if we look at even like go back to our HTTP example, we have 5 status codes, perhaps like HTTP 200, 400, 500, 300, and maybe even or none of those. And then so those are categories. They're not even status codes. You might have like 20 status codes. But let's just talk about 5 for now, because that's probably 5 that are important to you. And then say you're monitoring 100 endpoints, and then say your monitor, like maybe your product or system behaves differently depending on which country the user is in. So that's maybe say you operate in 100 different countries. And then you think about like server version. So you may have probably 10. It depends on your system, but maybe you've got 10 different versions of your server version rolled out, depending on a canary or a staging environment or a different region that you're operating. Maybe you're serving traffic out of different cloud regions. So that's kind of like status code 5 by endpoints 100, say, and then by another 100 for the cities, and then say you run in 6 regions. So and I've always relied on the calculator, so don't mind me while I multiply live the number here. So we're talking, that's already a very large number. Yeah, we're talking about 300,000 time series there. So that's 6 regions, 5 different status codes, 100 endpoints, and we're talking about 30,000. I put in 100 for different server versions, but 10 server versions is much more realistic. So that's 30,000 time series. You can imagine if you want to monitor on anything else, like user client agent, like whether it's Chrome or Safari, or whether it's iOS or Android on mobile, that's going to multiply that 30,000 again. So you very quickly get to these hundreds of thousands, millions. Now, granted, that is a pretty high cardinality metric, but you kind of, in these worlds we exist in, especially when you add container label to that, you might operate over 200 containers, and those containers might rotate as well. So if you're looking back over time, if you deployed your 200 containers twice, now there's 400 different containers that you could possibly be looking at the results from over a time window that you look at. So yeah, these numbers multiply very quickly, even for small companies. Netflix, at Monitorama, which is a monitoring conference held in Portland, Oregon, they mentioned that their system had 3 billion unique time series in it. And that was kind of level cardinality they were working with. At Uber, there were tons of experimentation going on. So we had tons of dimensions. Surge algorithms fluctuated dynamically, and that kind of depended on which region you're in. So we actually had 11 billion time series before I left the company to start Chronosphere, and it's an extreme challenge. I think when you like software developers become addicted to this stuff as well. Like at Uber, we had more than half of the engineering team daily visit with unique sessions, our monitoring tool M3, and interacting with the graphs or setting up alerts or checking on an experiment that they were running. So, our internal Google Analytics showed it was probably the most popular tool and most visited next to our deployment system at the company.
I can see how having this high dimensionality would enable you to surface problems that might be obscured if you average things together. But do you have the reverse problem if something was affecting all user agents in 6 countries across 5 code versions? You don't want to get, I can't do that number in my head, but you don't want to get 600 alerts when there is one problem. Do you have a way of grouping together so that you can collapse dimensions when it makes sense to do that?
Most definitely. That is a common problem that you've identified there that is hard to get right, I will say. Like, it depends on the tool you're using, but a lot of tools can do this really wrong, and you will get your phone blowing up. So the typical way that Prometheus, which is a popular open source monitoring and alerting tool, does this is, and M3 is really a scalable long-term storage and backend for Prometheus metrics. But the typical way in a Prometheus world you would do this is you set up your notification mechanism, the endpoints you want to be notified on. So one would be like PagerDuty, and then you essentially say that you want to group things always by alert name. So you author an alert, and if you don't group by an alert name, then you only get a signal yes or no whether alert's going off. So first you want to group by alert name, so you get an alert for each type of alert, and then you basically make sure that 600 cities are being affected or 100 endpoints. You're only going to get one alert for that, and so it'll group by. Everything else will get automatically grouped by. But then essentially you will want to retain that underlying cardinality data on the metric so that when you see the alert, it can show you all the different combinations of the dimensions that are currently exceeding the thresholds that you've set. And that helps weather the storm very quickly. But there's plenty of tools out there that don't do that, and you will see an explosion like you're talking about. And then you could go even further if you do want to get that alert broken down by different regions. You can do that as well and route the different regions to different people. So maybe there are different people on call for different things based on one of the dimensions of the metric that you're monitoring.
Where I want to get to in the time we have left is, Rob, you've done a great job so far at setting up the problem. And what I want to get to in the time we have left is a little bit about how you solve it in the monitoring platform. So let's briefly just spend a few minutes outlining either you could pick Prometheus or a generic monitoring tool that combines features of the common products. Say, what does a monitoring tool look like? And then we're going to ask, how do you solve this problem of having 6 million alerts without spending a excessive amount of cost on it? Let's talk about, what does a monitoring system architecture look like?
Yeah, that's a great question. And yeah, I think the general conception of how to do this is in flux. Like we live in the software development world. It's not like civil engineering. There's not a really well-oiled set of processes to do this. I will say there's obviously a lot of well-defined ways to do it, but it is changing more than in an industry like civil engineering, where you build something in a given way and that bridge is going to stay up. With monitoring, it is one of the more popular ways of doing it, especially in open source today, is using something like Prometheus, which will collect signals from your applications you develop, as well as it'll collect signals from the machines that your applications run on, so to get CPU, memory, and network signals from it. And those, and honestly, most generic monitoring systems will do this as well. It's just how they do it kind of differ. And then essentially, once you have that stream of information going from your application as well as your infrastructure to a single place, that's when you run into the problem of, okay, well, now how do I actually add capacity to the signals that I'm collecting? And just before we dive into that, one of the first things you want to solve, though, is how do you lower the friction for you to add a signal to the system that you set up. So you want to use client libraries that are popular, that are used by many people, and have some kind of backing that and maturity to them. So the Prometheus client library, for instance, works in every language under the sun. Prometheus also has this concept of exporters. So if you want to monitor a system that you don't own, there's likely an exporter for that. So, there's things like an Nginx exporter, a Redis exporter, a MySQL exporter, things like that. So you want to work out all your touch points and how to get signals into the system, lower that friction as much as possible, whether you're using a vendor or something like Prometheus and open source. And then once they're all kind of being collected in one place, you need to be able to use a system that can scale out. And so, depending on what type of organization you're currently, working for, or what kind of system you're developing, you'll have different needs, right? So if you never expand from if your system never gets complex enough to exceed a million or a million time series or so, or even fewer, or even a little bit more than that, one single Prometheus server is going to be absolutely fine for you. But we just did that math on that HTTP example, and we got to 30,000 very quickly. So you could imagine actually exceeding a few million pretty quickly. And Prometheus has certain ways where you can continue to use Prometheus even once you've exceeded a single server's capacity. You kind of separate out what you're monitoring. They go to separate Prometheus instances. And then when you're looking at graphs, you kind of like select which Prometheus server you want to get your results back from. But then, you may also just want to centralize all of this, because that's kind of talking about separating out the metrics to be collected by different things, and then kind of gluing systems on top to look at them and switching between them. But there's a lot of popular things in open source that help you actually send metrics to a central place, either most of the time through Prometheus if you're in the Prometheus ecosystem. So you kind of deploy these Prometheus servers and separate what they're going to monitor, and then they all send Prometheus will send data to a central long-term storage or central monitoring backend, and that's where M3, which is an open source project that the open source part of it I kind of worked on at Uber, and that's been available in open source since 2018. That's one of those central backends. There's also Thanos, which is another open source project in this space, and that Thanos project will back up its metrics to S3 or some other kind of object store in the cloud, whereas like M3 is more of an actual database. So it'll look like a database and give you access to metrics that it has on disk. So depending on your needs, you may lean to one centralized backend versus another. And I really think of these as gating functions, right? Like when you're getting started, Prometheus works great out of the box. When you're eclipsing one Prometheus server, you can still extend it a little bit further with just a few little tricks. And then when you go up even higher than that, and you've got developers that are kind of scaling, and you don't want any one team to have to manage their own monitoring infrastructure. You would look at something like Thanos if you're want something that to get you started, and just kind of historically back up the metrics and have access to them maybe at higher latency and all that, but still there with having the metrics in an object store. Or you look at something like M3 if you want super high reliability by replicating the monitoring data across availability zones in a cloud region. So at Uber, that was really important to us. An hour of gap of monitoring could have meant that could have been such a brand impacting event that we may as well have packed up our bags and gone home, right? So it really depends about like what kind of playing field you're currently playing in, and what makes sense to you depending on what you're doing, to which tool you reach for and what vendor you reach for. Some vendors are more expensive and easy to use. Others are cost effective and focus on scale. And then some have proprietary lock-in languages. Others will be more Prometheus and open source friendly, and use industry standards. So that's kind of the things that go on in my head when you think about how to like really think about this and dissect what your needs are depending on what you're doing.
All right, so to recap that, you have something which is compiled in, or very close to the stuff you're monitoring that can pull the metrics out, and then you need to transit them somewhere to central backend, and you store at least a certain amount of data in some kind of persistent store that keeps values either as long as you want or for as long as you can afford, because it could be quite a lot of data. That be the main architectural highlights.
Yeah, I think that's really what you need to start off with is what's going to be frictionless for you to use, and and which central backend do you want to kind of store it in, and what are your requirements and kind of budget as well for that.
I want to get into then the programming or engineering problem of, we talked earlier about you define alerts. Alert is some code which operates on a time series, and then it produces a value which might be pass fail, or it might be a value compared to a threshold, and then that's pass fail that determines whether the alert fires or not. Then we were talking about this cardinality, where you've got a big high dimension space, and that if any one single cell in this big high dimension matrix is going into a fail state, you need to generate an alert. So now, from a software engineering standpoint, how do you code that up, and how much memory and computation does it take to have 30,000 time series that you're simultaneously evaluating against this stream of 30,000 different incoming metric streams?
Yeah, I mean, that's a great question. It can vary a lot. Different monitoring workloads, even with the same level of cardinality, can be very different depending on like the time series functions you're applying on them. So for instance, if you want to do a time series query that sums all internal server errors up by city, that resulting matrix output is only the amount of cities you run in. So that's a lower number of time series. But if you want to then sum them up and group by not just by city, but you want to then group them up by iOS or Android version or something else, then that's a even higher resulting matrix output. So just to lay down some basic numbers to get an idea, if you're kind of collecting 10,000 time series per second, which, to be fair, if you're only going to actually take a point in time sample every 30 seconds, you're probably, even with like a cardinality of 30,000, it's not going to be 10,000 per second, right? It's going to be 1,000 per second. So if you're talking about 10,000 per second, various open source backends here, depending on what you're using, will use 10 to 20 gigabytes of memory, perhaps, and depending on how many queries you throw at it, so how many time series queries you're throwing at it, it could probably easily handle like maybe 50 to 100 alerts. And you're talking about maybe 4 or 5 cores. So you probably want like an 8-core machine for that. But that's really, talking about it from a Prometheus point of view. M3 is, similar levels of scalability and resource usage. These are highly advanced systems though. Back in the day, 10,000 per second with that type of hardware, not possible. There's a lot that's gone into that. There was TSZ, the TSZ compression algorithm that came out of Facebook that allowed for 11x compression on float data. That's talking about turning a 16-byte timestamp value of two 8-byte numbers into roughly, it averages out using this algorithm to 1.4 bytes per data point. So that compression ratio allows you to just store way more in memory. And, if you're frequently evaluating this, they're being pulled into memory a lot. So reducing, that memory usage is only possible with algorithms like TSZ. And then you've also just got much more sophisticated storage engines now, which, are smart and optimized for the right thing. You don't need ACID transactions and monitoring. You just have high volume. And so like kind of fully understanding that and refining the system to to kind of hyper optimize for that type of data structure and that type of collection has enabled us to really be able to do, to kind of like get to those sorts of numbers. And, a single M3 database node can do hundreds of thousands and, sometimes millions of data points per second. But we're talking about pretty large machines when we're talking about those kind of numbers. So, hundreds of gigabytes of RAM and 16 to 32 cores, that kind of thing.
I think this problem would naturally incline toward some degree of sharding, in that if you were, say, monitoring different regions, you might even have different groups of people who respond in North America, Europe, and Asia. And you could have entirely different monitoring backends, even though they're monitoring different segments of the same metric.
Right. Yeah. No, definitely. It's definitely a thing that leans it's natively can be partitioned, and I think that distributed systems in it's very key is about kind of partitioning and how do you map and reduce to query this type of data, and how do you even fairly distribute the workload. Like, you don't want some servers working much harder than others, because then you've got a micromanagement problem. An M3 under the hood actually will use a fairly good hash function to work out whether the combination of dimensions you're storing on which server it should be stored on. And that helps us actually get, like when we talk about a cluster that's doing 300,000 writes, if you have 3 nodes, it'll very evenly be doing about 100,000 each per second. So there's a lot that goes into making sure that these systems can scale out horizontally in a way that's sane without you having to micromanage the storage aspects to it. Prometheus does tend to be single node, as I kind of mentioned. It's a bit of a more decentralized storage model, but it is which you can partition yourself, and it is fascinating though how to operate these things.
You mentioned the open source M3, which you're involved in, and I covered that in your biography. Without saying exactly what it is, give us a proper introduction to M3.
Yeah, no, I can definitely speak more to that. So M3 is really a metrics platform at its core, and it's primarily a Prometheus long-term storage backend. And what I mean by that is, so when we talked about, what do you choose as your monitoring backend? These days, it's not just talking about a single monitoring backend. You may use different tools in your monitoring pipeline to pipe your data one or two or n places. But with Prometheus and M3, they kind of plug together nicely to give you basically a single scale out backend for the underlying data. So you can point all your alerts and your dashboards to M3, but use Prometheus, to kind of do the frontline collection of metrics before sending them to a central place. And that kind of, so M3 is really adding a layer to either an existing metric system, or if you're using Stasti or Graphite, which M3 also supports, it can ingest that type of metrics data directly. And so M3 is really what we like to think of as a central monitoring both database as well as aggregator. So M3 actually contains, unlike many other monitoring systems, an optional layer of aggregation you can perform on the signals that come into the system. And this was extremely helpful at Uber. So, some of these super high cardinality use cases we're talking about, we actually didn't care about the container sometimes, the container label. So the single container. If we're actually monitoring on telecom provider, we don't really care that the telecom provider will be down for all the containers, and if the telecom is experiencing an outage. So we would actually transform these metrics as they came in to the metrics platform in that central backend that M3 is. And so when we think about M3, it's really a time series database that's horizontally scalable at the bottom. It's optionally an aggregation, a streaming metrics aggregator, which can do transform on metrics that are coming in on the way in if you want to, which will help with even a higher level of scale. Is really for advanced users. And then it's the query service, of course, that sits on top that allows you to apply all these transforms. And you can kind of actually run all of these in one single process as you get started with M3, and then separate the roles out if you want to isolate the ingestion of metrics and the querying of metrics so that one huge query doesn't interrupt your incoming steady stream of metrics, things like that. So it's really a scale out multi-component metrics platform that you can kind of start getting started with just a single node, but then spin out the different components separately. And it was the center and the core of monitoring at Uber, and it's also the center and the core of the monitoring and observability hosted service that we provide at Chronosphere.
Rob, we're getting near end of time. Before we wrap up, would you like to share with listeners where they can find you or point them to any resources on the internet?
Yeah, of course. I would love if anyone's interested more on this topic. I share my thoughts frequently on it on my Twitter handle. That's twitter.com/Roskilly. So ROSKILLI.
All these will be in the show notes.
Brilliant. And then, just visit, if you're interested in M3 at all, you can visit m3db.io, and the Chronosphere, which is a hosted platform on M3, is at chronosphere.io, and you can find more about it there.
Rob Skilling, thank you for speaking to Software Engineering Radio. This has been Robert Blumen.
It's been fantastic, Robert. Thank you so much.
Thank you.
Developers, take your marks. It's time to upgrade your data platform to InterSystems Iris. It's time to deliver complex mission-critical applications in the fastest route possible. It's time to use any data from any source. It's time to embed analytics and create interactive user interfaces. So what are you waiting for? Choose your language, choose your tools, choose your environment. Collaborate, build faster, and deploy more efficiently. Done and done. Tomorrow's next breakthroughs are waiting for you today. InterSystems Iris Data Platform, the fastest way to build applications. Ready, set, code. Start coding for free. Visit intersystems.com/try to try Iris. Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.